Hi, everyone. So this is my first year as a fellow, and I'm really excited to be here. I just finished my first year at MIT, where I'm working on experimental quantum computing in the Engineering Quantum Systems Lab under Professor William Oliver. So I'll be talking to you all today about some work that my collaborators and I are doing. So, quantum computing is a technology that aims to represent and process information using the laws of quantum mechanics. So instead of bits, quantum information is encoded in quantum states called qubits that span a two-dimensional complex Hilbert space. Now, a crucial fact about quantum systems is that every time you add a quantum particle to the system, you have to take a tensor product, which means that the amount of information needed to describe that system scales exponentially with the number of quantum particles in that system. So even the most powerful classical supercomputers today can only simulate quantum systems up to a certain size. Quantum computers leverage this exponential scaling, as well as the phenomena of superposition and entanglement, to solve certain tasks that would otherwise be intractable classically. This has obvious applications in the realm of quantum simulation for fundamental physics, condensed matter, material science, quantum chemistry, but also for certain classical problems for which researchers have discovered a quantum algorithm that has significant speedups over the best existing classical ones, such as in the case of prime factoring or searching a database. Now, how do we actually build a quantum computer? Well, pictured up there is a device called a dilution refrigerator, whose sole purpose is to get a very small chip in the center of that tangle of wires down to millikelvin temperatures. Okay, why do we need to be so cold? Well, the kind of platform I work with uses superconductors to build quantum computers. But the superconductor we use, aluminum for example, only needs to be at about 100 Kelvin to be superconducting. So there's actually another reason that we need to be at these much colder millikelvin temperatures. We use these superconductors to build a kind of circuit element called a Josephson junction that is a sandwich of superconductor, oxide superconductor that functions as a nonlinear inductor that demonstrates macroscopic quantum behavior. We use these Josephson junctions to construct circuits that mimic atoms in their energy structure, and then we encode quantum states in these energy levels. There are many different kinds of circuits that can form a superconducting qubit. Pictured here are three of the most common kinds called transmons, which are made up of a capacitor, the big X pad, and the Josephson junction, which is at the bottom of the X pad and is too small to see clearly here. Together, the capacitor and the Josephson junction have the energetic profile of a quantum anharmonic oscillator, and we use the two lowest states of these oscillators as our computational basis, where we encode quantum information. Now, this energy transition is at microwave frequencies, which is why we have to operate it at about 20 millikelvin. Anything higher and thermal energy would overwhelm that frequency transition. So as you can see here, these superconducting qubits are actually quite big. They're on the order of 100 micrometers. Compare that to modern-day transistors, which are on the order of nanometers. This means we can only put so many superconducting qubits on a chip. So in order to build a scalable system, it has to be modular. And it's not just an issue of scalability, but also architecture. Classical supercomputers today are modular, and we want to be able to have different units performing different tasks in concert. So to build a modular system, we need to transfer information between them. And so we need to do this by transferring quantum information in the form of a single propagating photon between qubits on different chips. So that means we have a quantum state encoded in a qubit. We need to transfer it into a photon, which is a propagating wave packet that holds that information. That photon flies through the waveguide, and we need to catch it into a qubit on another chip. Now, there's a problem with this, which is that if you couple a qubit to a bidirectional waveguide, the photon will split. Half the time it'll emit in one direction, and half the time it'll emit in the other. This makes it impossible to route photons between qubits if you want to use just a single bus. But we've worked on an approach where we place two qubits on a waveguide, a certain distance apart, and we initialize them in an entangled state with a certain phase. And as that entangled state emits at both points from both qubits, the photon propagating through the waveguide acquires a phase that cancels perfectly with the phase from the entangled state. So we end up with the photon constructively interfering in one direction and destructively interfering in the other, allowing us to emit a single photon in the direction of our choosing. This directional emission allows us to place multiple chips along a waveguide and route photons between any pairs of our choosing, creating a quantum network with all-to-all connectivity. With this approach, we have a path towards building a scalable modular quantum computer. Thank you.